Okay, folks, in this video, we are going to look at the solutions to series and parallel circuit problems 11 through 15. Well, let's take a look at number 11. We have a 22 ohm lamp and a 4.5 ohm lamp are connected in series. So that's important to know. They're in series and placed across a potential difference of 45 volts. What is the equivalent resistance of the circuit? Because this is a series circuit, I know that the equivalent resistance is just equal to the sum of the individual resistors. So we take 22 ohms, add 4.5 ohms, we get 26.5 ohms or 27 ohms to two significant figures. Part B for question 11 is asking what is the current in the circuit. So I am looking for the current for the entire circuit. So I am going to use the voltage going across the battery, which is 45 volts. And I need to use the equivalent resistance. And I know that according to Ohm's law, the current is equal to the voltage divided by the resistance. So 45 volts divided by my equivalent resistance of 26.5 ohms is going to give me a current in the circuit of 1.7 amps. Part C asks, what is the voltage drop across each lamp? Now, because this is a series circuit, I know that the current is going to remain the same across all the lamps. And to find the voltage going across just one of the lamps, I need to use the resistance of that lamp, not the equivalent resistance. I know I can use Ohm's law to find the voltage. So the voltage going across the first lamp is going to equal my current of 1.7 amps times the resistance of that lamp, which is 22 ohms, which is going to give me a voltage of 37 volts. For the voltage going across the second lamp, I'm going to multiply my current, 1.7 amps, times the resistance of the second lamp, 4.5 ohms. When I do that, I'm going to get a voltage of 7.7 volts. One thing I do want to point out here is if I add up the voltages going across each lamp, 37 plus 7.7, I'm going to get 47.7 volts, which is very, very close to the overall voltage of the circuit. There's a little bit of a discrepancy there due to rounding errors, significant figures, but it is very, very close. So again, a good way to double check your work. Part D asks, what is the power dissipated in each lamp? So if I'm looking for the power, I know that power is equal to current times voltage, P equals IV. So if I want to find the power dissipated by the first lamp, I know I need to use the current, which is the same for all lamps, 1.7 amps, times the voltage of that lamp, which is 37 volts. So 1.7 amps times 37 volts will give me 63 watts. To find the power dissipated by the second lamp, I multiply my current by the voltage of the second lamp, which was 7.7 volts. So 1.7 times 7.7 is going to give me 13 watts. Problem 12. They want us to answer the following questions about figure 3. So they want to know, what should the amp meter read? So here is the amp meter right here. So we're looking for the amperage or the current for the entire circuit. Now this is a series circuit. Remember, I know it's a series circuit because the current only has one direction or one path it can follow. It comes out of the battery. It's going to have to go through the 35 ohm resistor, then through the 15 ohm resistor, and then back through the battery. The characteristics of a series circuit is that it only has one path that it can follow from one side of the battery to another. So let me just erase a couple of these marks here. So if I'm looking for the current for the entire circuit, and again in a series circuit I know that the current is constant at all points in the circuit, I need to know the overall voltage of the circuit and the equivalent resistance of the circuit. So I'm given the voltage of the circuit as 10 volts. So now I just need to find the equivalent resistance of the circuit. Well, I know that the resistance of each individual resistor, and if I can find the equivalent resistance of each individual resistor, I know I can find the equivalent resistance. So the equivalent resistance is going to be equal to the resistance of resistor 1 plus the resistance of resistor 2. So 35 ohms plus 15 ohms is going to give me an equivalent resistance of 50 ohms. And now I know what the equivalent resistance is. I can use Ohm's law to calculate the current. So 10 volts divided by 50 ohms is going to give me 0.20 amps. Part B asks, what should voltmeter 1 read? So we're looking for the voltage across the 35 ohm resistor. I know that the current going across the resistor is going to be 0.20 amps. We got that from the first part of the problem. And because it's a series circuit, I know that the current is going to be the same at all points in the circuit. So to find the voltage, we simply need to use Ohm's law. So I know it's the current times the resistance. 0.2 amps times 35 ohms is going to give me a voltage of 7 volts. Part C asks, what should voltmeter 2 read? So we're looking for the voltage across the 15 ohm resistor. We still need to use Ohm's law as we did before. I know the current is going to be the same as the prior resistor because the current doesn't change in a series circuit, and I just need to use the resistance of this resistor. So 0.2 amps times 15 ohms is going to give me a voltage across this resistor of 3 volts. Part D asks, how much energy is supplied by the battery per minute? First thing I need to do, I'm going to have to convert my minutes to seconds. I know that 1 minute is equal to 60 seconds, and I want to find the energy. I know that energy is equal to power times time, and I know that power is equal to current times voltage. Remember, P equals IV. So I know the current is 0.2 amps. The voltage of the battery is 10 volts times 60 seconds is going to give me 120 joules of energy. Problem 13, we're given a circuit diagram, and we are told that the voltage across the 35 ohm resistor is 70 volts. The first thing that they want us to determine is which of the 3 resistors is the hottest. So we have 3 resistors. One is 15 ohms, another one is 35 ohms, and the third one is 50 ohms. So if we're going to determine which one is the hottest, we need to know which one is generating the most power. And I know that the power is equal to the current squared times the resistance. Now in a series circuit, the current is going to be the same across each of the resistors. So to get a higher value for power, I need to have a greater resistance. So the resistor that has the greatest resistance is going to generate the most power and is going to run the hottest. Think of what a resistor does. It resists the flow of the electrical energy. And the way it resists the flow of the electrical energy is by converting some of that energy to heat. The greater the resistance, the more heat that's generated. You can think about it in terms of light bulbs. If you have a 20 watt light bulb and a 100 watt light bulb, which one is going to be the hottest to touch? It's going to be the 100 watt light bulb. Same kind of idea here. Part B asks which resistor is the coolest. So we have the same general idea as the previous part. Remember that because the current is the same across each of the resistors, in order to get a higher value, or in this case a lower value for P, we have to have the smallest possible value for R. So the smallest resistance that we have in this circuit is the 15 ohm resistor. So the 15 ohm resistor will give us, or will be the coolest, because it is resisting the flow of the electrical energy the least. Therefore, it's converting less of that electrical energy into heat energy. Part C asks, what will the amp meter read? So here is our amp meter right there. Oops, I'm not sure if that came up, but let me try that again. And because this is a series circuit, I know that the current is the same at all points in the circuit. So if I can find out how much current is going through the first resistor here, that's going to be the same value as the current flowing through the amp meter. So I know that the voltage going across that resistor is 70 volts, and I know that the resistance for that resistor is 35 ohms. I know the current is equal to the voltage divided by the resistance. That's just Ohm's law. 70 volts divided by 30 ohms is going to give me a current of 2 amps. Part D asks, what is the power supplied by the battery? So in order to find the power supplied by the battery, I need to know the equivalent resistance of the circuit. I need to know the resistance of the entire circuit. So to find the equivalent resistance, because this is a series circuit, I simply have to add my resistances together. So 35 ohms plus 15 ohms plus 50 ohms is going to give me an equivalent resistance of 100 ohms. And I know that the power is equal to the current squared times the resistance. And we can get that formula right off of the Ohm's law diagram that Mr. Broderick went over with you in the PowerPoint. So 2 amps squared times 100 ohms is going to give me a power of 400 watts. Problem 14, we're given another circuit diagram, and we know that the voltage across the battery is going to be 110 volts, and they're asking which resistor is the hottest. Now here we have a parallel circuit, whereas in the previous problem we were dealing with a series circuit. In a parallel circuit, I know it's the voltage that's going to be the same across each branch of the circuit. So if I want to compare the power and the resistance relative to the voltage, my formula now is going to be P is going to equal V squared divided by R. Now my power and my resistance are not directly proportional to one another the way they were in my previous formula, P equals I squared times R. In that other formula, P equals I squared times R, both power and resistance were in the numerator. Now I have power in the numerator and resistance in the denominator. So the bigger my value is for resistance, the smaller my value for power is going to be, because now they are inversely proportional, because one of them is in the numerator, one of them is in the denominator. So in order to get the greatest value possible for power, I need to use the smallest resistance possible. So now the smallest resistor is going to run the hottest, because that's going to give me the most power. So now the 10 ohm resistor will be the hottest. Part B is asking which resistor is the coolest. So once again, we're going to take a look at our formula P equals V squared divided by R. Remember, we're using this formula because we know that the voltage is going to be constant along each branch of the circuit. So I want to compare the power and the resistance with something that isn't going to change, which is the voltage. And because the power and the resistance in this formula are inversely proportional to one another, because the power is in the numerator and the resistance is in the denominator, the greater my value for R, the smaller my value for P, right? The bigger R gets, the smaller P gets. So in order to have the smallest value for power, I need to have Part C asks, what will amp meter 1 read? So we're looking at the current going through the entire circuit. And I know I want to know the current for the entire circuit because my amp meter isn't along one of the branches for the circuit. It's actually where all the branches combine and goes straight through the battery. So I know that in order to find the current for the entire circuit, I need to know the voltage for the entire circuit, as well as the resistance for the entire circuit. The voltage I'm given, 110 volts, so that's the voltage going across the battery. So that's the voltage going across the battery here. And I know that in a parallel circuit, the voltage is going to be the same across each branch of the circuit. But now I need to know the equivalent resistance. And I know that the inverse of the equivalent resistance is going to equal the sum of the inverses of the individual resistors. And in order to put that in our calculator-friendly version right here, much easier to put into the calculator than adding fractions up, I know that the inverse of the 20 ohm resistor plus the inverse of the 50 ohm resistor plus the inverse of the 10 ohm resistor, and I take the inverse of that sum right there. That is going to give me an equivalent resistance of 5.88 ohms. And I know that the current is going to equal the voltage divided by the equivalent resistance. That's Ohm's law. So 110 volts divided by 5.88 ohms is going to equal 19 amps. Part D asks, what will ammeter 2 read? So here is ammeter 2 right here, and I know that is the ammeter that is connected to the 20 ohm resistor, I should say in series with the 20 ohm resistor. I know according to Ohm's law, the current is equal to the voltage divided by the resistance. I know my voltage is 110 volts. Because in a parallel circuit, the voltage is going to be the same across each branch of the circuit. And I know in order to find the current going through the 20 ohm resistor, I need to use just the resistance of that individual resistor. So 110 volts divided by 20 ohms is going to give me a current of 5.5 amps. Part E is asking, what will ammeter 3 read? We have ammeter right here. We're going to solve this the same exact way we solved the last part. We just need to use the resistance of this resistor. So we know that the current is going to equal the voltage divided by the resistance of resistor 3. So 110 volts divided by 50 ohms is going to give me 2.2 amps. Part F asks, what will ammeter 4 read? We have ammeter 4 right here in series with the 10 ohm resistor. So to find the current going through ammeter 4, we need to use the 10 ohm resistance. So 110 volts divided by 10 ohms is going to give me a current of 11 amps. Finally, on to problem number 15. Thought problem 14 was never going to end. Who makes these problems up? Don't go blaming Mr. Broderick. It wasn't him. These are still my homework assignments. So I guess I have no one to blame but myself. And you have no one to blame but me either. So there we go. All right, let's take a look at problem number 15. We have the same circuit diagram that we had in the previous problem, but now we've changed it up a little bit because now we know that ammeter 3 is reading 0.40 amps. And they're asking, what is the battery voltage? So we want to know what is the voltage going across the battery. Well, again, this is a parallel circuit, so I know that the voltage is going to be the same across all branches of the circuit. So if I find the voltage on one branch of the circuit, I know it'll be the same across all branches of the circuit and the battery as well. So for this branch of the circuit, I know both the current and the resistance. So now I can use Ohm's law to find the voltage. So the voltage is going to equal my current, which is 0.4 amps, times my resistance, which is 50 ohms, and that is going to give me a voltage of 20 volts. For part B, we're asked, what will ammeter 1 read? Here is ammeter 1 right here. And we've already been asked this in the previous problem. In problem 14, part C, asked the same exact thing. And we have the same circuit diagram. One thing we haven't changed are the resistances of each resistor. We've changed our current and our voltages, but we haven't changed the resistors. So this is going to be very similar to part C of problem 14, but we're going to end up with a slightly different answer because of the differing voltages and currents. But to find the the current going through ammeter 1, we're going to need to find the equivalent resistance of the circuit. And that's actually going to be the same as in the previous problem, because again, we haven't changed our resistances at all. So to find the equivalent resistance, I know that the inverse of the equivalent resistance is going to equal the sum of the inverses of the individual resistors. And we are going to put that in our calculator-friendly format. We're going to substitute in our 3 resistors. We're going to take the inverse of each of those, add those up, and then take the inverse of that sum. And we are going to get an equivalent resistance of 5.88 ohms, just like we did in problem 14. But now when we plug that equivalent resistance into Ohm's law, I now have a different voltage. So now my voltage is 20 volts, and I divide that by 5.88 ohms. I'm going to get a current of 3.4 amps. What? Holy cow, I'm boring. I put myself to sleep. Whoa. All right, we're almost done here. Couple more to go. Let's take a look and see where we're at. Part C of problem 15. What will amp meter 2 read? All right, here we have amp meter 2 right here. And I know that according to Ohm's law, the current is going to equal the voltage divided by the resistance. I know that my voltage going through each branch of the circuit is 20 volts. I know the resistance of this resistor is 20 ohms. So 20 volts divided by 20 ohms is going to give me a current going through ammeter 2 of 1 amp. All right, part D. We're just about there, almost done. So we just have one more to go, and then we can all go to sleep for real. Who am I kidding? It's only 11:30. I'll be up for at least a couple more hours doing these videos. All right, so for the last part of this, we want to know, what does amp meter 4 read? So we're looking for the amperage going through amp meter 4, which is wired in series with our 10 ohm resistor. So once again, using Ohm's law, I know that the voltage of 20 volts divided by my resistance of 10 ohms is going to give me a current going through amp meter 4 of 2 amps. All right, guys, that's it for problems 11 through 15. Keep reviewing these. The test is coming up in a couple of days. If anybody has any questions about these problems or any of the other problems that we've been going over, come into one of our Google Hangouts that Mr. Broderick or I are doing, or just send one of us an email and we'd be happy to answer any questions you guys have.